Okay, hello guys. So my name is Kshitij, and today we have the new topic with us, which is clock domain crossing or clock domain design. Okay, so let's deep dive into it. What is it? So we'll first go into the basic of it. The first video is pretty much covers the basic part of it. What actually the CDC means, right? So it's multiple clock domain design understanding is quite essential for a ASIC TE. Okay, so in most often practical design scenarios, the multiple clock domain designs are used, and it is quite essential to understand and validate the legal converging states of signals passing from one of the clock domain to another clock domain. So it's not like there is only one clock in your entire project. There are different clocks, different modules work on different clocks. So for that we have the concept of CDC. Fine. So yeah, so assume that there are two registers which are reg A and reg B here as shown. So the reg A works on clock 1, reg 2 works on clock 2. Two different clocks are there. Some data is coming from some combination logic or something as data into reg A, and then it is taken as an output, which is data out 1, and given to reg B here. Okay, but there arises a problem when the signal, which is the data out 1, goes from one domain belonging to clock 1 to another domain belonging to clock 2. What are those problems and what specifications do we need to consider? That we'll see. So CDC is a quite simple approach to design a single clock domain logic. So when single clock domain is there is no concept of CDC. It is quite clear. But when multiple clocks are there, then arises the issue. So what happens is that if all the flip-flops in the design are clocked by a single clock source, then the design is said to be a synchronous design, right? But when different clock sources are used in the design, then it is actually a asynchronous clock domain design. So in modern SoCs, the SoCs which we design today doesn't work on a single clock. It works on different clocks with different frequencies too. Okay, so the main concept which arises the concept of CDC is the data transfer from the slower clock domain to the faster clock domain. Okay, from faster to the slower clock domain. So this is pretty self-explanatory. Okay, so we have one kind of image which will kind of make it more clear to you. The data or the control signal crosses from one of the clock domains to another clock domain and is described by CDC, which we have already discussed. So one part is the slower, one clock is slower and one is the faster. Okay, as a Verilog example of this, the simple module which works on a single clock, okay, is this. So we have a single clock, right, and data in is there, clock is there, one output reg is there for flip-flop. Okay, and at the positive edge of clock, the data in is going to the data out 1, which infers your first flip-flop, this reg A, and at the same positive edge of clock, the data out is going to the data out 1 is going to the data out, which is inferred by this one, data out non-blocking statements, data out 1. So this infers your second flip-flop, which is reg B. So this is the Verilog code for if you want to synthesize in this manner. So you can take a look at it. But this describes the single clock source. So as a waveform point of view, this is the clock. Okay, data in is coming, say after some kind of propagation delay, the combinational delays which are there in the paths that has been introduced. So some delays there. So the data in is captured at this positive edge of clock, right, as shown here. which goes to data out 1, right? And then at the next stage of the clock, the data this is sampled, the data out 1 is sampled here, and the kind of the signal propagates. So this is quite a rough diagram, which is not that what we can say, it's not up to the mark which I wanted to tell you. It is roughly, there is no concept of clock domain crossings where we are trying for single clocks. Okay, no such problem occurs. Now if we want this kind of design where we have one clock 1 and one clock 2 which are being fed to the two different flip-flops, so how we can write its code, Verilog code. So we have two clocks with us, clock 1 and clock 2 in the port list, then inputs then outputs, then two always blocks we have to write, right, because there are two different events. Those events are clock 1 and clock 2. So at the event of clock 1, the data in 1 is going to data out 1 here as shown, and at the second event, wherever the clock 2, the positive edge of clock 2 comes, data out 1 is going to the data out. So this data out 1 is going to the data out. So in this manner we can write the Verilog code, but the data out, this middle one, sorry, this last one is in the metastable state for one clock cycle. This occurs. So how it occurs, and before going to the metastability kind of problem, we will have separate video on the metastability, the setup and hold timings, but as of now I assume that you have some basic knowledge about it. So let's discuss the basic of setup and hold. So setup time is defined as the minimum amount of time before the clock active age arrives. So the data must be stable before for it to be latched correctly. So whatever data which is being given to your D input, that data need to be stable at some logic, whether 0 or 1, any one of them need to be fixed before the positive edge of clock comes. So before how much time it should be fixed, that is defined by the setup time. So this is the TS or TSH, whatever they have written. So this is your clock. It's not an ideal clock, so we can say this is the clock in which this flop is working. So before the positive edge of this clock, the data must be stable for this much amount of time, which is defined by the TS. Okay, so this is the data, so it is stable for before the positive edge of clock at amount of TS, right? So this TS is the setup window for the clock, positive edge of clock, that is defined by the setup. So your data shouldn't change like this. So this data is, for this case, it is changing inside the setup window, inside this slot. This shouldn't happen, then there is a setup violation. But if your data is changing in this manner, so this is okay, because this is outside the setup window, right? So this doesn't infer any kind of metastability, but okay, that's the concept of setup. And when, what's hold time? Hold time is defined as the minimum amount of time after the clock's active age during which the data must be stable. So this we have defined for this setup time before the positive edge of clock. Same for the hold time. This is the positive edge of clock. Okay, we have just drawn it here, and this is the time TH. Okay, as shown here, this is that TH. So your data must be stable for that amount of time too. So this data, which is 1, this is your data, right? D is your data. So this is stable at 1 for this window too. Okay, this TH is the window, right? This much. So this is at 1 for TH amount of time. It is going to 0 after the this TH. Okay, this is not up to the mark, so we can just assume that this is going in this manner. Okay, the image is not that good, but we can assume that. But if your this D is going to 0 inside the H window, TH window, as shown, as drawn here, right? This one. So it is before this TH, okay, in the inside the TH window it is going to 0. That's why there is a hold time violation. So this shouldn't happen. So your data shouldn't be it shouldn't be unstable inside the timing windows of setup and hold time. So this is the metastable state, where your state is neither 0 neither 1, it is something middle. This is what it shows. It's not 1, it's not 0. So the output of flip-flop is undetermined, so we can't predict. So the scenarios results, the scenario which we have discussed now, it results into the synchronization failure between multiple clock domain designs. It is due to different clock frequencies and different phases of the clock in the design. So we will discuss this part, frequency part, in the later slide. So according to this diagram, right, the clock 1 and clock 2 diagram, this is its waveform. So this is the clock 1, and data in is given as same as the previous waveform which we have discussed. It is going to 1 after some time, and then data out is here going to 1 at this edge of clock, as we have discussed here. As we have discussed, because this positive edge has passed of clock 1, so it is now going, the data out is 0, which is sampled from data in, and then at this positive edge of clock it is sample this data in at the flop, and so the data out 1 goes to 1, right? Then there is another clock 2 which is kind of tracing this data out 1. This act as an input to this reg B. So at this positive edge of clock 2, it is taking this data, right? And this data is actually quite inside the setup window of the clock 2. That's why we can't predict whether the data out is 0 or data out is 1. It's not proper. That's why the metastability issue is there, and the data out is not 0, it's not 1, it's neither 0, it's neither 1. So when clock 1 and clock 2 are there, so the data out is either 0 or 1, that we can't say. You can see here, say assume that the setup time is this much. This is the setup window for the clock 2, and your data, which is the data out 1, is changing inside the setup window. This should be stable. Before we can say that this should be 0 if we wanted before the setup window, but it is not. Okay, similarly for hold time, it is not stable at all in the setup and hold windows. That's why there is the issue of metastability. Okay, so what was the requirement here is that the data 1 should be there at least for setup and hold time to pass. Say this is the TR and this is the TS, so this should be 1 for some amount of time, the data out 1. So that is not happening here, that's why the metastable state is there. So metastable state of the design is not a stable state of the design, so that the data output, which is the data out, is fed to another logic, then the output from the another logic is other logic is unpredictable state or invalid logic state. So when you are feeding this kind of data out to another logics, which is just after this reg B, so that's not good. An unpredicted state you are going to give to your another modules and another logic, so that disrupts your logic. That's why we don't want such things to happen. So it is essential to have the synchronizers in your data path and control path. So the issue of this metastability can be resolved by adding the level synchronizers. The first part of the synchronizer, or the simplest one, is the level synchronizers. So that we will see where while sampling the control signals from one clock domain to another clock domain. So what we do, we just add one flip-flop before reg A, before reg B and after reg A, which is sticking at the clock 2. So let's see what impact it gives. So this is the module, the Verilog file. You can very easily read that. Change is just here. So actually it is sometimes called double flip-flop logic, which kind of eradicates the issue of metastability, right? So it's same, just there is the change in this part. Two always blocks are also written and two flip-flop logic is written. Okay, so this is the final diagram. So it's same as we have discussed. Clock 2 is there, B and C resistors are ticking, and one clock 1 is there. Okay, so let's see this diagram. So now this is your actually clock 1. Okay, this is your clock B. Yeah, so where the issue arises. So say as an example, if anyone asks you about what is metastability and what is CDC and what kind of things we need to take into consideration, so you can take this example. This is the best example to explain anyone in the interview or something. So you can take this as example, draw this waveform and just explain to him or her that what is the issue, why we have used the synchronizers, and how the CDC issue is being resolved by using the level synchronizer. The first and the most basic one is the level synchronizer. There are much more designs, much more complicated designs that we will see in the later videos. Okay, so the data out one, which is this one, is changing from 0 to 1 at this edge. Okay, so this is the positive edge of clock 1, which is taking this data out. So data out 1 has changed from 0 to 1. That same data out is acting as an input to your B, right? So the output of B is data 2, and which is ticking at the clock 2. So this is my clock B or clock 2, anything you can say. So now what happens, that this is the setup window which is given by this yellow shade, right? So change of 0 to 1 is happening inside the setup window of clock 2, right? So what does this means? That is a setup violation, and due to this the data out 2 is actually metastable. So it is not 0 neither 1. If this data out 1 waveform was quite like this, okay, as what I have drawn, so you can see it is 1, data out is 1 inside the setup window. It's not changing from 0 to 1 inside the yellow shaded part. So it means that your data is stable inside the setup window. There is no problem of metastability, but obviously it is still 1 for your hold time also, th. So no setup and hold violation. But if as per our scenario which we have drawn earlier, it is changing inside setup window, so there is metastability. And now this metastability stays for just one clock cycle. Why one clock cycle? Because in the next edge of this clock, the data out 1 is stable at 1. So you can see this is the positive edge, and say this is the setup window, TS, right? So this is 1 for all amount of time, so there is no setup and hold violation. So this data out 2 is set now settled to 1. It is not in metastable state, right? So as this is stable to 1 at this amount of time, or we can say at this clock 2 edge of the clock 2, this positive edge of the clock 2, the data out 3 can easily take this data out 2, right? So it can take, and there is no issue in the data out 3 at the output side. So there is no problem at that side when we have introduced uh, one flop in between. So that actually eradicates your CDC problem, but still there are some drawbacks of this. But as a basic point of view, this kind of thing eradicates your problem.